Hello, and welcome to the video accompaniment for sections 2 and 3 of chapter 3. In this video, we'll be talking about some methods of proof. In particular, we'll cover direct and proof by contrapositive. Now, I don't think it's strictly necessary that you read through the section before this video. If you'd rather watch the video first and then read through the section, you might find that more helpful. Whatever works for you. In this video, we'll start by giving some definitions for even, odd, and rational numbers. Remember, definitions are going to be very important because those give us a starting off point for proving things, and that's really the only way we know what something is if we know its definition. And so that these three are very commonly used, even, odd, and rational numbers, and we'll look at definitions for those and then apply them in the following slides. And we'll cover these two methods of proof, direct proof, proof by contrapositive. We'll understand how they're done in general and how they're applied, as well as look at a few examples of these. And lastly, we'll talk about, along the way, understanding when we should apply these methods. As well, we'll understand how to prove a biconditional statement. And so that'll be something that involves both direct proof and potentially proof by contrapositive at the same time. Well, really not at the same time, but working in tandem with each other. All right, let's get started. All right, so like I said, we should cover a few often used definitions. So an even integer, we say an integer is even if it can be written as x equals 2k for some integer k. So as long as we can find this k, such that our integer is twice that number, then we'll know it's even. Similar for odd. This time, if it can be written as 2k plus 1 for some k, then we know it's odd, right? We know it's one more than an even number, and therefore it must be odd. These should look familiar in our definitions for even and odd integers that you used previously to write, to use set builder notation to describe these sets. So those should both look familiar. And then we also have rational numbers. This should look familiar too. Remember, a real number is rational if it can be written as a ratio of two integers. So if r equals a over b for some integers a and b, where b does not equal 0. So just a quick example, right? Why this works, -8 is even. That's an even number because -8 is 2 times -4. Some people have asked this in the past, is 0 an even number or 0 an odd number, or do we not consider it even or odd? Well, now with this definition, we can answer that. This is one way definitions can be very helpful, is it handles these sort of like edge cases or these sort of weird situations. This one's not actually that weird. 0 is even because, well, we can write it as 2 times 0. So it's definitely even rather than odd. 11's odd because we can write it as 2 times 5 plus 1. So it's 1 more than 10, which is an even number. And -7 is odd since we can write that as 2 times -4 plus 1. That works too. Rational numbers, we could say 0.75, that decimal is a rational number because 0.75 is the same thing as 3 divided by 4. 3 and 4 are both integers, and 3 is not equal to 0. And so that fits the definition. We could also write it in some other ways, but in any other way we write it, it'll look like an even or an integer divided by an integer where the numerator is not 0, or sorry, where the denominator is not 0. And then even something like, I know I get questions like, oh, rational numbers are just decimals that end at some point. But that's not necessarily true, right? We know numbers like 1/3 or 1/9 have infinite decimal expansions. For example, -0.111 repeating is rational because -0.111 repeating is equal to -1 over 9. So again, that's -1, an integer divided by 9, another integer, and 9 is not 0. And so that fits the definition. All right, so we'll use these along the way with some proof examples that we'll see in a second. So the first method of proof we're talking about in this video is direct proof. So this is proving something directly. And oftentimes what we'll be proving is a universal statement attached to an implication. So for all x and s, P of x implies Q of x, something like that. So think about what needs to be shown in order to prove this is true, we need to show that this implication holds for every x and s. And so in order to show this implication holds, what we'll do is we'll assume that p of x is true, right? We'll assume the hypothesis and show that the conclusion has to follow. So this makes sense with our definition of implication, right? The only time this could be false is if the hypothesis is true and the conclusion is false. And when the hypothesis is false, we don't need to do anything. We know the implication's true. So the only cases we need to look at are when the hypothesis is true. Hence, we'll assume the hypothesis and show the conclusion follows, right? If p of x is true, then q of x must be true. So let's just take a look at a quick example of proof of a direct proof. So here we'll prove the following statement: if x is even, then x squared is even. This could also be stated: every even integer, or rather we could say it like the square of every even integer is also even. We could say it like that, but here it's phrased nicely for us as an implication. All right, so how can we prove this? Well, this is just like this statement. We're proving something's true for all integers. So if the integer x is even, then x squared is even. We have to prove this implication. And so what we'll do is we'll start by assuming our integer x is even. So I'm going to go over here and write proof. And actually, you know what? I'm going to use yellow. So proof. Why is this true? So we'll start by assuming the hypothesis. Let x be even. And we know we want to end up with this statement: x squared is even. So remember back to our definitions of even. If x is even, that means x equals 2k for some integer k. Let x be even, then x equals 2k for some integer k. And we know we want to get to the statement x squared is even, so we want to, now that we know what x looks like, we've written here an arbitrary even integer, it just looks like 2k, we want to make some statement about x squared. So let's investigate what happens if we square x. So x is even, x is 2k. So x squared then would be 2k squared, and we can compute that. That's the same thing as 4k squared. Okay, we're almost there. Notice that I can write 4k squared as 2 times 2k squared, and that 2k squared is even. So I'll say here, since 2k squared, oh sorry, not 2k squared is even, 2k squared is an integer. Right, if k is an integer, we know k is an integer, then when I square that I'll get an integer, and when I multiply by 2 I'll get an integer. Those sort of things we can just kind of take for granted. So since 2k squared is an integer, then x squared, which is, we know now, 2 times 2k squared. So look at what we've done. We've written x squared as 2 times some integer, and that integer being 2k squared. So x squared is 2 times 2k squared. We know that that must be even then, because 2k squared is an integer. And that's it. So we assumed x was even. We used the definition of even. We investigated what x squared would then be, and we saw that we could write x squared as 2 times another integer. Hence, x squared is even. So we assumed the hypothesis and showed the conclusion, and our proof then is done. And so that's not too bad. There's our first example of a direct proof of an implication. We'll take a look at another example in the next slide. Since we just did an example involving even integers, I thought it was appropriate to look at an example involving odd integers. So let's take a look at this. We want to prove the statement, if x and y are odd, then x plus y is even. All right, let's try proving this. So again, we're proving a universal, right? This is over all integers, right? For all integers, x and y, if x and y are odd, then x plus y is even. So this is a universal statement with an implication. If x and y are odd, then x plus y is even. So we'll go ahead and assume x and y are odd to start off with, right? We're doing this the same way. So let x and y be odd. And just like we did in the last one, we knew x was even. We could write it as 2k. Now they're odd, so we can write them as 2 times some integer plus 1. So let x and y be odd. And I'll say x equals 2k plus 1. And y equals 2j plus 1 for some k and j in the integers. So notice here that I had to use both k and j. So what would be the case? What if I wrote y equals 2k plus 1? Just use the definition with, using the same integer k as I did with x. So what this would mean is that x and y are actually equal to each other in that case. If I were to write y equals 2k plus 1, then x is also equal to 2k plus 1. Those two things would be the same. That would imply that x equals y. But that's not our assumption. We're not assuming that x and y are equal, just that they're both odd. And so that's the reason why this doesn't work. We need to use a different integer. It might be the case that k is equal to j, but again, we want to leave this as general as we can possibly be. And so writing this y equals 2j plus 1, that includes the possibility that j could equal k, but it doesn't require it, right? It doesn't necessarily mean that. And so be careful with that when you have two things that are both odd, or one's even and one's odd. That you'll want to keep this in mind to use separate variables unless you know for sure that they're equal to each other. Okay, so now we've assumed that x and y are odd, and we've written them out using definition of odd. And we want to investigate this number x plus y. So let's compute that. Then x plus y equals 2k plus 1 plus 2j plus 1. And let's just simplify that a bit. That's 2k plus 2j plus 2. And look at what I can do here. I can factor a 2 out of everything. 2 times k plus j plus 1. So why would I factor a 2 out of this? Well, I want to end up with the statement x plus y is even. And I know that even means it has a factor of 2, that I can factor 2 out of the whole thing, right? I can write it as 2 times some integer, and look at what we have here. K plus j plus 1 is an integer. So I'll just say, lastly, that since k plus j plus 1 is an integer, right? If k and j are integers, their sum is an integer, and then I add 1 to that, that'll still be an integer. Again, this is more of an obvious statement that we don't really need to prove separately. It's okay just to use that. It's not too much of a logical leap to get to that. It's an integer. It follows that x plus y is even. So we assume the hypothesis and prove the conclusion. Hence, this statement is now proven. So I'll draw a little tombstone to indicate we're done with the proof. All right, let's take a look at another example, this time involving rational numbers. Proving statements about rational numbers is very similar to proving statements about even and odd integers, in the sense that we know what an arbitrary rational number looks like. Just we know what an arbitrary even number looks like, right? 2 times some integer. And we know what an odd integer looks like, 2 times some integer plus 1. Rational number we know looks like an integer divided by an integer where the denominator is not 0. So let's take a look at of a direct proof involving rational numbers. If x and y are rational, then x plus y is rational. So while we take for granted the fact that if I have two integers and add them together, I get another integer, that's sort of more obvious than this statement. If x and y are rational, then their sum is rational. It might seem obvious, but really there's a proof we need to do to get to this. So let's take a look at how that might work. Proof. So if x and y are rational, so suppose, here we'll assume the hypothesis, suppose x and y are rational. And just like we did in the other ones, if they're rational, what does that mean? Well, it means we can write them as an integer divided by another integer where the denominator is not 0. Since we have 2 here, we know we'll have 2 different ratios of integers. Then, let's say x equals, what do we want to call this? How about a over b? And y equals, let's use c over d, where, and we want to specify that we know those things are integers and their denominators aren't 0 to accommodate the definition, where a, b, c, d are integers and b and d are not equal to 0. It's okay to list things like that when it's clear what we're talking about. Okay, so now we've assumed the hypothesis and we have written them as arbitrary rational numbers. We want to make some, we want to show this conclusion about x plus y, so we want to investigate that sum just like we did in the last one. So x plus y then would be equal to a over b plus c over d. And keep in mind our end goal here, we want to show that that sum is rational. So I'd like to write this sum, a over b plus c over d, as a rational number. So I need to write it as an integer divided by an integer and make sure the bottom's not 0. Well, how do we add 2 fractions? We can find a common denominator and then add their numerators. So I could write this as a d. So I'll multiply the first fraction by d over d, ad over bd, and then I'll multiply the second fraction by b over b. So I'd get cb over bd. So all I did there was I found a common denominator, bd, and it's always going to work that you can multiply the 2 denominators together. That'll give you a common denominator. Just remember to change your numerators in that case to make sure these fractions are equivalent. And now we can add across the top, now that we have a common denominator, we have AD plus CB over BD. And so it looks like now we've written this as a rational number divided by a rational number. So let's go ahead and double check that. AD plus CB will certainly be an integer. CB is an integer, since A, B, C, and D are integers. And BD, we need to make sure the denominator is not 0. So how do we know that it's not 0? Well, we took 2 non-zero numbers and multiplied them together. So we're actually using this zero product property of integers again. And BD is not equal to 0 since B is not equal to 0 and D is not equal to 0. Hence, putting it all together now, x plus y, which we wrote as AD plus CB over BD, is rational because we wrote it as an integer divided by another integer where the denominator was not 0. And we made sure all those things were satisfied in this second to last line. All right, that's a proof. So now that we've talked through proving something directly and how to do that, let's talk about one more proof technique, proof by contrapositive. So again, we'll be interested in proving a statement, a universal statement like P of x implies Q of x, so proving some implication is true for all integer or for all x in some set S. Remember that an implication is equivalent to its contrapositive, right? So this statement I wrote there is equivalent to the statement for all x and s. Not q of x implies not p of x. So when it's convenient to do so, instead of proving the implication directly, we can prove the contrapositive instead. And since the contrapositive is also an implication, right? It's the implication not q of x implies not p of x. We can follow the same idea for a direct proof, right? We'll assume not q of x and show that not p of x must follow. So the real trick here is identifying when we should use a proof by contrapositive. And really we should answer the question, why would we even do this? If we can just show something directly, why would we use the contrapositive? Well, really, we wouldn't. If we can show something directly, most mathematicians would favor that. They would try the direct proof first, and if that's not working, they'd try the contrapositive. So why might it not work? Well, sometimes assuming p of x, right, that's the first step in showing this implication p of x implies q of x, sometimes assuming p of x, it doesn't give us enough leverage. It doesn't, you'll see what I mean in a second. But what I mean is we don't know what an arbitrary element satisfying p of x looks like. Right? With even integers, we knew what those looked like. So assuming p of x was fine, we knew we could write it as 2k, right? 2 times some integer. But sometimes it's not going to be that easy. And in those cases, that's when we'll want to use a contrapositive. So when we don't have enough leverage by just assuming the hypothesis, we can try this. So let's see an example of where this might be done. So we'll take a look at the following example. Prove the statement, if x squared is even, then x is even. All right, so notice, before I start proving this, I want to notice what I was talking about just a second ago, that assuming the hypothesis doesn't give us enough leverage. So let's just say we tried to show this directly, tried to do a direct proof on this. We would start by assuming that x squared is even. Let x squared be even. Then we could write, right, following the same stuff, we could write x squared equals 2k for some integer k. But where would we go next? We want to make a statement about x, so maybe we take square roots, something like that. We could say x equals square root of 2k. And does that really give us much information? X equals square root of 2k. It's not written as an even integer, right? We can't factor a 2 out of this necessarily. And so we're really kind of stuck here. There's really no way to show that x is even, which is what we want to do. And so this is the case where a direct proof really won't work out. We really sort of need to use the contrapositive. And so the contrapositive of this statement then would be, so what we'll actually prove is that if x is not even, so if x is odd, then x squared is not even, so x squared is odd. So this is what we'll actually use. And here we can see we have the leverage, right? We know what an odd integer looks like. We can square that and then verify that that is odd. And so this is what I'm talking about with leverage. So let's go ahead and prove this statement. Like I said, we'll assume that x is odd. So assume x is odd. Then we can write x equals 2k plus 1 for some integer k. And we can, this is hopefully starting to seem a bit formulaic. That's good if you're starting to see patterns in the proofs. That's the next step of understanding proofs, is seeing patterns in proofs. So what do? We want to investigate x squared, so let's square x. So x squared then would be 2k plus 1 squared, which is, we can square that out, that's 4k squared plus 4k plus 1. Okay, and we like to come to the conclusion that x squared is odd. So what I'll do here is I'll factor out a 2. Notice we have 4k squared plus 4k. I can factor out a 2 from those 4s. So I can write this as, I can write this as 2 times 2k squared plus 2k So I factored 2 out of those first two terms, plus 1. And hopefully you know the next step. I just want to verify 2k squared plus 2k is an integer, which it is, so I'll just write it. So I'll say since 2k squared plus 2k is an integer, it follows that x squared, which we wrote as 2 times 2k squared plus 2k plus 1, that we've written this as 2 times some integer plus 1, and so we know that this must be odd. And there's our proof. So again, we proved the contrapositive of the implication rather than the implication itself, and we had to do that because we just didn't have enough leverage by assuming the hypothesis. All right, let's take a look at another example. So we keep using even, odd, and rational numbers for examples. Here we'll take a look at a proof using proof by contrapositive that doesn't involve any of those three things. So prove the statement if for all real numbers x, if x cubed plus 3x squared plus 2x plus 1 is less than or equal to 0, then x is strictly less than 0. So again, we might want to use a contrapositive here, because if we just assume x cubed plus 3x squared plus 2x plus 1 is less than or equal to 0, it'll be hard to solve that for x and make some statement about x, right? We have a cubic polynomial. It might not even have real roots. It'll just be difficult if we start with that assumption. So rather than that, we will instead, what we'll do is we'll prove the contrapositive. Contrapositive here being if x is not strictly less than 0, so if x is greater than or equal to 0, then this polynomial x cubed plus 3x squared plus 2x plus 1 is not less than or equal to 0. We'll show that it's greater than 0. So that's our goal. Assume x is greater than or equal to 0, show that this polynomial is strictly greater than 0. All right, we're ready to prove it. So I'll start with my assumption with the contrapositive. Let x be greater than or equal to 0. Then, so I'd like to say that this polynomial is strictly greater than 0. I want to first establish some facts. So if x is greater than or equal to 0, then certainly x cubed is greater than or equal to 0. 3x squared will be greater than or equal to 0. 2x will be greater than or equal to 0. And that's sort of it. I know if x is greater than or equal to 0, then those three things have to be true. And now if I put them together, hence x cubed plus 3x squared plus 2x plus 1. So I can say that this is greater than or equal to, since I know each of these three things is greater than or equal to 0, I can replace those with 0 and know that I'll know that the left side is greater than or equal to the right side. So this is the same thing as greater than or equal to 0 plus 1, or just 1. So if x is greater than or equal to 0, this polynomial has to be greater than or equal to 1, and 1 is strictly bigger than 0. And that's what I wanted to prove, right? That this polynomial, notice what I have here, this polynomial is strictly greater than 0. And so there I have my proof. So in all these examples we've seen so far, we've been proving implications, but keep in mind that biconditionals are made up of two implications. So if we want to prove a biconditional, say p of x if and only if q of x, then we really need to show two implications hold. We need to show that p of x implies q of x. So there's one sort of proof. We need to show that. And we need to show that q of x implies p of x. So we need to show two sort of directions, right? a forward direction that p of x implies q of x, and a backwards direction that q of x implies p of x. Now sometimes, and actually this happens quite often, one of the directions it'll be hard to show directly, and we'll have to use a contrapositive on it. So what that means is we'll end up proving something like just maybe directly showing the forward direction that p of x implies q of x, and then using a contrapositive on the backwards direction. So we'll show that not p of x then implies not q of x. And so we'll end up showing maybe these two things rather than the original two things. We'll switch one of them out with their contrapositive. So this is sort of a mix between a direct proof and a contrapositive. So we'll take a look at how this works in an example. So in this example, we'll use a proof by contrapositive as well as a direct proof to prove a biconditional. In particular, we'll prove the following statement. The integer n is odd if and only if n squared is odd. So notice here I need to show two things. N odd implies n squared odd. And I need to show that n squared being odd implies n is odd. And that'll prove the biconditional, right? That'll show that n is odd if and only if n squared is odd. And so that's the idea, that's the setup. Notice that this first one, we'll do a direct proof on this, because assuming the hypothesis will give us enough ammunition to show the conclusion. But in the second one, n squared being odd, remember, assuming something like n squared being odd or n squared being even, that's not enough leverage to show that n is odd. And so for this one, we'll do it by contrapositive. So let's prove this thing. I think we're ready to prove it. Now sometimes when I'm proving a biconditional and when other people are proving a biconditional, you'll sort of notate that you're going to show the forward direction and then show the backward direction. So what I'm going to show here is I'm just going to write in quotes an implication going this way. And all I'm saying by this is, hey, I'm about to prove the forward direction of this biconditional. So for the forward direction, I said we're going to use a direct proof. Let n be odd. Then we know we can write it as n equals 2k plus 1 for some integer k. And we can investigate n squared. So n squared then would be 2k plus 1 squared, which is 4k squared plus 2k, plus 4k plus 1, which we know we can write as 2 times 2k squared plus 2k plus 1. And since 2k squared plus 2k is an integer, n squared, which is equal to that, is odd. So that takes care of the forward direction. Now I'm going to start a new assumption, right? That's sort of done with that, with n being 2k plus 1. I'm sort of done with that. And now I'll start on the backwards direction. So I'll just show an arrow going the other way and start on that. So I know we're doing this one by contrapositive. Maybe I'll make a statement by saying like, oh, by contrapositive. We're going to do this one by contrapositive. You don't have to write that. If I see that you're assuming the opposite of the conclusion, I'll know that it's a contrapositive. But just to be clear, that's what we're doing for this one, by contrapositive. So we'll start with the assumption that n is even. N be even. Right? We're showing we need to assume the opposite of this and show the opposite of that. So let n be even, then n equals 2k for some integer k. So, and I want to make a statement about n squared. So n squared is 2k squared. You can write as 4k squared, or 2 times 2k squared. And now we've written it, it's twice an integer. I'll just say that in words. Since 2k squared is an integer, n squared, which is 2 times 2k squared, is even. And so I showed, right, if n is not odd, then n squared is not odd. And so that takes care of the backwards direction, proved by contrapositive. And since I have both now, I can conclude my proof with a little tombstone. I did the forward direction directly and the backwards direction by contrapositive. Okay, that's it for this video. Remember to read through a lot of proofs that are in the book. There's a lot more examples in the book that I haven't gone over, so make sure to look at those and practice the problems in the back of the book.